Now I want to talk about one of the most important things in entire quantum mechanics and entire physics. And this is harmonic oscillator, but quantum version. So classically, we can let's start with a classical harmonic oscillator. Harmonic oscillator is a system where you have a wall, you have a spring, and you have a mass, right? So this is M. There's a spring constant K, and you know F is equal to minus Kx, so-called Hooke's law. And F is equal to m times A, so Newton's second. So this is going to give you m times A is x double dot is equal to minus k times x. So in classical physics, you are also solving a second order differential equation, but as you can see, it's much simpler than x double dot plus k over m. X is equal to 0. And our job is to solve x as a function of t. How many people know how to solve this equation? I think everybody, yeah, right? This is kindergarten stuff. So this is going to be something like a cosine omega t plus maybe a phase. And the picture is, I have a potential. So this is u of x. So this is x, and I have some energy that I give to the particle. So like this, and the particle just goes back and forth, right? If you want, we can also put it like this, E. This is E. Maybe I can. So these are classically allowed region, whereas this one, like here or here, classically forbidden. And these are so-called, this one is, maybe I can write it here. So this one is turning point. Turning, or classical turning point. So why is this an important problem to study? So we want to study this problem quantum mechanically for several reasons. First of all, there are in physics we are modeling the nature with potential. There can be some potential like this, right? It could be arbitrarily more complicated, maybe something like that. And I can put my particle here, and I know F is equal to minus du dx. If my particle is here, from here, so this is my, if you want x, this is u of x. So if my particle is, for example, here, what is the direction of force based on this? To the right or to the left? To the left, right? And if I put my particle here, similarly, the force du dx is minus is plus. A positive force is going to be to the right. Or if I put my particle here, right, there's a peak here. And if I calculate du dt, this is negative, and there's an overall minus is plus. There's a positive force on this direction. Similarly, if I put it here, there'll be a force like this, and similarly, force like that, and force like this. So these are stable minima. So these are unstable. And typically what happens is like a quantum particle, like an electron, there's like a potential landscape, and it kind of equilibrates over time. You don't need to do anything. Like for example, it just comes here and gets trapped here, right? It just bounces back and forth. And you can just choose some energy for electron here, and it's going to be here, there, right? And I can say, okay, here, rather than studying this complicated potential which I have no control of, I can approximate it. I can approximate it like this. So this is approximation potential, and approximation is going to be U of x is going to be equal to, so this is, let's call this point x naught. So u of x naught, and I'm looking at small deviations from u of x naught, and the first one is like derivative of u at x naught times x minus x naught, or 1 over 2 factorial second derivative of u x naught at x minus x naught squared, something like that. So what is the value of derivative at the minima? So here, what is this object? So this is 0 because this is by definition of minima. And I can shift. So I can absorb this in the definition of my energy. If you want, I can take my 0 with respect to there, right? We can change potential any way we want. And I can choose my coordinate system so that this x is x naught. Then this is going to be 1/2 k x squared, where k is going to be u double x naught, okay? Which is like a harmonic oscillator. Another example is like you can consider, like for example, two atoms, and atoms, you know, may form molecules. For example, this is atom A, so this is atom B, and for reasons we are going to come soon in this course, if you are patient, the potential is something like that. So this is u of r. It is going to be at, like, when they are infinitely separated, they don't interact, like something like that. When they are infinitely close, they are going to repel infinitely strong, and you are going to go from one to other like that. And you can, for example, approximate here, like with like an harmonic oscillator, right? These two, and the bound state of these two molecules is going to be the solution of harmonic oscillator, and whatever the energies you have inside is going to be given by the solution of harmonic oscillator potential. Good. Any questions?
No, I don't understand.
So I like whenever there is like a minimum, I can approximate it, right, with Taylor expansion. So what I'm saying is like this blue line, right? It is a little bit complicated, and I cannot solve it anyways, even if I can model it. So there is like a optimum like separation here, like x naught. These two molecules have like a optimum separation. They don't want to be like infinitely separated. They don't want to be infinitely close. And around this infinite optimum separation, I just model it with harmonic oscillator, right? And then I say this molecule is connected to the other, so this is A and this is B. And if I want to look at, for example, energy eigenstates and like energy levels, I'll just solve the harmonic oscillator problem. Maybe quickly, I think there's like a nice exercise, and we have a little bit time. So let's first start with the Broglie approach. So here is my potential. And I choose like an energy level like this, E. And in the case of like an infinite box, right? We were trying to like, this was the size of the box here. Like, let's say this is L, and we were trying to fit integer number of wavelengths inside the box, right? So here, if we are in the middle, it's going to be something like this. But due to these like potential at the end, maybe there will be some like damping at the end. But to lowest order, I can approximate this like a box. So let's consider E is equal to, like, let's consider the potential energy, 1/2 kx squared. Then these classical turning points, x is going to be 2e, and this is 2e divided by k, and I'll take the root. And what, according to de Broglie, what I need to do is like, I take this 2x, which is the size of the box, and I try to fit integer wavelengths like this, right? Half a wavelength, right? It can be half a wavelength, 1 wavelength, 3/2 wavelength, and so on. Then from here, lambda is going to be equal to 4x divided by, so this is 4x divided by n. So I want to look at my kinetic energy, which is p squared over 2m. Of course, in this case, it is not free particle. It's like going to be inside a like a wall. It's like kinetic energy is not p squared over 2m. But I want to make an approximation without like difficult calculations. And for p, I'm going to use h over lambda. That's the de Broglie relation. And lambda is this. So this is going to be h squared over, so this is h squared over 2m lambda squared. And this is going to be h squared over 2m. Lambda squared is n squared over square root of 4 is 16 x squared. Good. But the total energy is kinetic energy plus potential energy. So E total, and in the harmonic oscillator, it comes out to be twice the kinetic energy or twice the potential energy. So E is p squared over 2m plus potential energy. And I'm going to write it like, I'm doing approximations anyways. So it's going to be 2 times this object. But now x is written in terms of E, and this is also E. So let's substitute. So this is equal to, let me write this entire thing. And for 1 over x squared, I'm going to write k over 2e. I'm just copied this, right? Is that clear? And this is an equation in terms of E, so then E squared is equal to h squared over 32m. So I got h squared, I got 2m, I get this. So this is k, so this is n squared. So E is going to be equal to h over 32 k over m. Okay, k over m is going to be my omega, right? So this is this one. So this is omega, and this is n. And I want to write it like h bar. Oh, yes, yes. Root 32, yes. Omega.
Doesn't omega equal to square root of k over?
Yes, like this, right? Okay, good. Now I think it takes, right? So this is, I take the square root of both sides. I have h, I have root k over m is omega, and I want to write it like h bar omega. So k over m, but I take the square root of both sides. So this is E is equal to, so E is equal to this. So I want to write it like h bar, and h bar is 2 pi, so I'm going to write it 2 pi. So at the end, so this factor I calculated 2 pi root 2 is like something like 1.5, which actually doesn't matter, times h bar omega times n. And this actually happens to be not too far from the exact solution, right? So the exact solution, before we come to that, is like we can see like equally spaced energy levels. This is different from particle in a box. In the case of particle in a box, the energy level spacing was going with n squared. Here we have like equal spacing, which is given by h bar omega. There is like a 1.5, but we are doing approximation anyways. So a couple of notes before I give you the exact solution. Maybe let's write the Schrödinger equation, and because I'm not going to solve it anyways, let me give you what the exact result will look like. So full Schrödinger equation is h bar squared over 2m d square psi d x squared plus 1/2 m omega squared x squared psi is equal to E psi. So how do we solve differential equations, right? So this one, for example, is much more complicated than anything we considered so far, and you are going to solve it with so-called power series. But let's try to like develop intuition for a few minutes. We solve differential equations by substitution, so we need to find something to substitute. And what can we substitute? First, here's my potential. Right? This is u of x is equal to u of minus x. Then I have the symmetry condition we discussed at length last time. So solutions should be first of all symmetric. And for a given energy like this, right, this is classically forbidden. So we don't have any problem with non-zero amplitudes, but they should better decay like this. And I also want at this to approximate the ground state. And the ground state we know from like our previous examples, there is like no node in the ground state. And the closest thing I can like draw for ground state is something like this. If I were to, for example, consider like excited state, it would be something like this. But let's only consider the ground state. And what can this be, right? So this is exponentially decaying, and it can be something like e to the maybe minus au, but this is not symmetric. So let's make it minus alpha u squared. And there will be maybe like an overall normalization, and this is my ansatz. Right? So if you substitute this to there, let's do a substitution and see what this gives us. Minus h bar squared over 2m. So a, if I take the first derivative, it's going to be minus alpha times 2u e to the minus alpha u squared. And if I take one more derivative, I can take derivative of this, which is going to be minus alpha times 2 e to the minus alpha u squared minus, or I can take the derivative of the second thing, it's going to be 2 alpha u squared e to the minus alpha u. Okay, u is x, so this is x, sorry about that, x squared. So these are x. I guess you guys are also a little bit tired. Nobody warned me. So this is x. And this is the second derivative. And close it. Plus 1/2 m omega squared a, okay, exactly the same thing, is equal to some energy times exactly the same thing. Now let's cancel the factors, cancel a's, and there's no derivative anymore because I already took it, so cancel these, cancel these, and so I have, so this one is going to cancel, like, let me write it, h bar squared alpha over m plus h bar squared alpha over m, actually minus, because of that minus h bar squared over 2m for alpha x squared, alpha squared x squared, right? Yes. Plus 1/2, so there's like x squared, I deleted here, 1/2 m omega squared x squared is equal to E. And what do I want? I don't want, like, energy is the eigenstate, there should be no x in energy, right? I cannot have like position dependent energy, so I want to cancel this with this, and for this to happen I must have 1/2 m omega squared should be equal to h bar squared over 2m for alpha squared, so I cancel these, and so this is, and I'm trying to choose alpha, so this is going to be m squared, this is divided by h bar squared, and this is 4, then my alpha is going to be just, this is, take the root, this is 2, right? And let me write alpha on the other side. So this is my alpha. So my wave function is something like this. Psi of x is some a times e to the minus alpha x squared. And I know alpha in terms of m, omega, and h bar. And how can I find a for this? How do we find the overall constants in wave functions? Normalization. So normalization 1 should be equal to dx psi squared. This is going from minus infinity to plus infinity, and this is going to be a squared minus infinity to plus infinity. So this is dx e to the minus. So when I take the square, it's going to be 2 alpha x squared. So how many people know how to take this integral? Gaussian, right? Maybe I can show you real quick. So it's not hard. So I want to write, like, the motto of today is like write everything in dimensionless form and then do either numerical or analytic calculation. So what I'll do is I'll plug in root 2 alpha here and divide by 2 alpha here, and I'll call u square is equal to this one is going to be u square 2 alpha x square, or u is going to be root alpha x, right? So du is going to be root 2 alpha dx. So then this is going to be a square 2 pi du, it's also going minus infinity to plus infinity e to the minus u squared. How many people know how to take the integral of this one? So, yes? Huh? This is? Even function, but how do you take the integral? What is the result? So the way, okay, here's a trick. If nobody showed you, I am going to be the first one. So what you do is you write it twice, and you take square root. And because these are dummy variables, I can write whatever I want. So I want to write x for here, y for here, right? And now I'm going to combine x and y. So this is going to be, okay, let's pull this guy out of the way. So if you combine x and y, x squared and y squared, when you sum up, it's going to be r squared. And dx dy is going to be r dr d theta, right? And so this one is rotational symmetric, so this is going to give you a 2 pi factor. And now if you do the substitution one more time, right? So this is e to the minus u type of integral divided by what? Because of this 2, and there is a minus 1 from 0 to infinity. Okay, this is going from 0 to infinity after the change of variables, and it's going to give you 1/2. And this 1/2 is going to cancel this. So the result of this integral is going to be a square root 2 alpha. Okay, this is 2 alpha times root pi. Then a, if you write the expression for alpha, you are going to find m omega divided by pi h bar to 1/4. Here's your normalization. Okay. And one more thing. So we found alpha, we found a. There's one more thing we need to find, and this is the most important thing. What is left? Energy, right? And energy, you can see these two cancel, and the only thing left is this one. So let's take this and see what this is going to give us. So this is our energy, but this is the ground state. Let me write E0 for this. So this is going to be h bar squared over m, and alpha was what? We found alpha here. So this is my alpha. So m's cancel, h bars cancel, and this is 1/2 h bar omega, and which is non-zero as it should be, right? So non-zero ground state energy. Because of like a Heisenberg uncertainty, we have to have like a 0-point energy, ZPE. So we have that satisfied, and it seems to be like a simple h bar omega. And from our like earlier discussion here, like this silly discussion gave us like a spacing like this, right? It was spaced with h bar omega, and the lowest energy seems to be 1/2 h bar omega. I think it wouldn't be too much of a guess to think full energy spectrum to be something like n plus 1/2. Okay, and that's exact solution. Any questions? So actually you can, like, if you have plenty of time to take integrals, you can actually calculate all of these states. For example, for the first state, so we can like the ground state is like something like this, psi 0 of x. The first state, what could it be, right? In the first excited state, we need to have like a node, so it should look something like this. There's like a node, and it should do something like this, right? This is a node. And for this to happen, maybe you can substitute something like this, like x e to the minus alpha x squared. And by exactly the calculation we did, by repeating these lines, you can actually find the first excited state. And for the second excited state, you are supposed to have two nodes. What can it be, right? Maybe something like ax squared plus bx plus c, but it has to be symmetric, so you have to kill this one, substitute it, find the coefficients, and you are going to find all of these levels one by one. But the more systematic level is so-called like power series method, and I think some of you are already learning it this semester, right? You can solve any differential equation by expanding it in power series, and nobody is learning differential equations this semester. How many people are taking mathematical methods 1? How many people took mathematical methods 1? You guys already took it. Okay. So that's where you were supposed to learn it. So that's fine. So at the end, the picture is something like that. Again. So here is my potential. So this is U, and this is X, and this is generally how people show this. So this is the ground state. This is the first excited state. This is the second excited state, dot, dot, dot. So this is h bar omega over 2. So the spacing here is 1/2 h bar omega 2. This is the 0 point motion. But all the others are spaced with h bar omega. This is h bar omega. Maybe I can finish with one last note. So in the, remember in Planck's derivation of leg body spectrum. If you remember, he took energy level spacing to be h nu, right? He was saying that the modes on the cavity walls were quantized. These vibrations were quantized, and only these vibrations can couple to light. And this difference now is going to be h bar omega, because energy level spacing here is h bar omega. But of course, later we know that Einstein came and like said, no, light itself is quantized, which is another story. Here there is like a 0 point motion, which is not accounted in the Planck picture, but this is not a big deal, because here we are saying that these vibrators are on the wall, they are quantized, and they only, whenever they transition from one level to another, they emit light. And that light is going to be, E is going to be some n times h nu, which actually makes a good case to justify that. And lastly, exact solutions are known. So exact solutions are so-called harmonic polynomials. So they are like sines and cosines. We studied they are like sines and cosines for the quadratic potential, and they are something like that. Maybe I can write it psi of x. Some, let me call it an. So this is hn of y e to the minus y squared over 2. So this is harmonic polynomial. So this y is a scaled variable. So this y is equal to m omega over h bar, m over h bar times x. And they look exactly like what we thought it would be from the de Broglie discussion. All right, I think that's it. Thank you, and I'll see you guys next time.